Welcome to today's deep dive, everyone. When you're sitting at your computer, you type a prompt into an AI, and
Mhm.
the response you get just feels, I don't know, completely instantaneous.
Oh, yeah, it feels almost magical, right? Like there's a little person inside the machine typing back to you.
Exactly, yeah. You type a question, and this beautifully articulated answer just materializes on your screen out of nowhere.
Right. But that seamless experience you're having, it's basically a highly polished illusion. It masks this incredibly heavy industrial multi-stage pipeline happening in the background.
Right, and that is exactly our mission for today. We really want to deconstruct that illusion for you.
Yeah, we're going to break it all down.
And to do that, we are using this absolutely brilliant visual flowchart.
hmm
It was created by Level Up Coding and Nikki Siapno.
It's such a fantastic piece of source material. I mean, it literally maps out the underlying architecture of large language models in a way that just clicks.
It really does. So we are going to trace the journey of just a single piece of data. We'll follow it from this massive, dusty server warehouse through this crazy gauntlet of algorithmic machinery all the way to the glowing screen of your laptop.
And I really love the visual metaphor that Level Up Coding chose for this diagram. It sets the stage perfectly for understanding what these systems actually are.
Yeah, describe it a bit for us. It's a really unique look, right?
It is. The artwork is this captivating blend of, well, heavy industrial factory equipment. Like, you see literal pipes, towering server banks, control panels with physical
Right,
sliders.
very gritty and mechanical.
Exactly. But then that industrial stuff intersects with this stark biological imagery because right in the center of the diagram is this glowing mechanical brain.
The contrast is just immediately striking when you look at it because, we have these geometric cold metal boxes on the left side of the diagram, right?
Yeah.
And they're feeding directly into this pulsing, organic-looking structure on the right side. It's weirdly unsettling, but cool.
Well, that aesthetic choice is super deliberate. It captures the fundamental nature of a large language model
How so?
because it visually represents the intersection of cold, brute force data processing and the compelling illusion of organic thought.
Ah, right. Because it feels like a brain, but it's built like a factory.
Precisely. By mapping the process as an industrial assembly line, the diagram strips away all the mystique. It forces us to examine the so-called magic as just the final output of a highly structured mechanical progression.
Okay, so let's actually follow that progression. Let's start from the very beginning of the pipeline, which is located at the top left of the diagram.
Right, the raw harvest.
Yeah. The visual here features these massive multi-tiered server banks. They literally look like towering silos in a factory district.
Yeah, very industrial.
And the function labeled right above them reads, aggregates and cleans large text data sets.
The visual scale of those monolithic servers is critical here. They're drawn with these thick, heavy pipes leading out of them.
Which symbolizes the sheer volume, I imagine.
Exactly. It symbolizes the incomprehensible volume of human text required to even initiate the training of a foundational model.
Like, how much text are we actually talking about here?
Oh, we are looking at the ingestion of massive swaths of the entire internet. We're talking billions of parameters, petabytes of raw text.
Wow. Okay, so when we talk about scraping the internet at that kind of scale,
Yeah.
the term aggregates makes perfect sense. You're basically just vacuuming up everything.
Right, exactly. A giant digital vacuum.
But the second part of that label, the part that says cleans, that's where the mechanical reality really sets in for me.
Oh, absolutely. That's the hard part.
Because if you vacuum up the entire internet, you aren't just getting beautifully written, peer-reviewed academic papers or like classic literature.
No, not at all. You're pulling in a ton of garbage.
Right. You're getting fragmented code, broken HTML tags from defunct websites, just endless strings of SEO-optimized gibberish.
Yeah, just raw, messy data dumps. And the definition of clean in this context is what dictates the structural integrity of the entire downstream system.
Okay, unpack that a little bit. What do you mean by structural integrity?
Well, if the ultimate goal of the architecture is to learn human language, the raw input has to be structurally sound.
Makes sense.
If you feed a neural network a steady diet of broken HTML and random ASCII characters, it doesn't know any better. It trains the network to view that broken HTML as acceptable, mathematically valid human communication.
Oh, wow. So it would literally start talking to you in broken code and weird symbols.
Exactly. The machine has no inherent common sense. So this cleaning phase is all about identifying what actually constitutes usable linguistic structure and discarding the noise.
Okay, I think of it kind of like harvesting wheat for a massive bakery. You can't just throw the whole muddy field, dirt and rocks included, straight into an oven, right?
Right, that's a great analogy. You have to gather the wheat, which is the aggregation, and then strip away the dirt and rocks, which is the cleaning.
Right, but scaling that cleaning process across petabytes of text, that requires its own layer of automated heuristics. Like, you obviously can't have humans manually deleting broken links all day.
No, that would be impossible. The system has to autonomously decide what is language and what is just digital detritus. And that autonomous filtering is essentially the first major point of failure or success for a model.
Really, the very first step is that critical.
Oh, yeah. If the filtering algorithms are too aggressive, they might strip away valuable stuff like colloquialisms, niche technical jargon, or really complex linguistic structures.
Which would leave the model with a super sanitized, almost robotic vocabulary.
Exactly. But on the flip side, if the filters are too weak, the model ingests all that noise we talked about. And that corrupts its eventual understanding of syntax.
So it's a massive balancing act right out of the gate. The quality of this initial scrub directly dictates how smart that glowing brain is going to be later on.
Yep, you nailed it. The brain is only as good as the food it eats, so to speak.
Okay, so once that massive data set is scrubbed and the noise is stripped away, the diagram shows the clean data traveling through a thick blue pipe.
Right, moving on to the next phase.
Yeah, and it goes into this specialized, long yellow processing machine. It honestly looks like an industrial smelter or something.
Yeah, that marks the transition from the raw harvest stage into the refinement stage.
Okay, the refinery.
Exact.
Because the raw text, even if it's stripped of its broken HTML, is still just raw text. It's words on a page.
Exactly. And the pipeline now has to translate human language into a medium that the machine architecture can actually read and process.
And the diagram lists 3 distinct sequential functions happening inside this yellow processing unit. It says deduplication, normalization, and tokenization.
Right, those are the 3 key steps. And after they're executed, the processed data flows into a central blue database cylinder for storage.
Okay, let's dissect deduplication first, because
Yeah.
on the surface, stripping out duplicate sentences just seems like a simple storage-saving measure, like freeing up space on your hard drive.
It sounds like that, sure. But given the sheer scale of the internet, deduplication actually serves a much deeper architectural purpose. It's not just about saving space.
Really? What's the main purpose then?
It's entirely about managing vector weighting. Machine learning models understand the world through frequency and repetition.
Okay, frequency and repetition.
Yeah. Think about how the internet is actually built. You have standard boilerplate legal disclaimers, right? Or viral meme templates, or just repeated website navigation menus.
Oh, like the contact us or terms of service links. They're on literally every single web page.
Exactly. Those phrases appear millions, maybe billions of times across millions of domains.
So if the model is learning the relationships between words based on how often they appear together.
Feeding it the exact same sentence 10 million times is going to severely skew its understanding of reality.
I see. It would encounter a phrase like, terms and conditions apply, a billion times more often than it encounters a phrase like, photosynthesis requires sunlight.
Right. And without deduplication, the model's underlying mathematical weights would shift massively toward that legal disclaimer.
Oh, wow. So it would begin to treat those specific strings of text as like the most fundamental, universally connected concepts in the human language.
Yes. It would essentially overfit on boilerplate text. Every time you asked it a question, it might just start spouting out a privacy policy.
That's wild. So deduplication basically prevents the algorithm from getting brainwashed by the internet's echo chambers.
That's a perfect way to put it. It forces the data set to represent a more proportional view of human language, rather than just a distorted frequency map of internet repetitive junk.
Okay, that makes total sense. So that proportional data set then moves to the second function inside the yellow machine, which is normalization.
Right, normalization. Because human language, especially online, is incredibly chaotic in its raw form.
What do you mean by chaotic? Like slang?
Slang, sure, but also we use disparate encodings, varying capitalization rules, entirely different formats for numbers, dates, currencies, all of that. Normalization standardizes the text.
Ah, okay. So it strips away the superficial formatting variances so the machine can evaluate the actual semantic meaning.
Exactly. For example, if a user writes AI with periods, or AI without periods, or artificial intelligence, all in lowercase.
The model needs to recognize those as the exact same conceptual entity, not 3 totally distinct variables.
Yes. Normalization reduces the dimensionality of the data. By forcing our weird, irregular human expression into a standardized baseline format, it saves computing power.
Because the neural network doesn't have to waste computational resources trying to distinguish between trivial formatting differences. It just knows they mean the same thing,
Right. And this streamlining is the final preparatory step before the text hits what is arguably the most complex and vital function of the refinery.
which is tokenization.
Tokenization, yes.
No, tokenization is a concept that gets thrown around constantly in tech circles, but I feel like its actual mechanical execution is really misunderstood by most people.
Oh, totally. It's a very abstract concept.
According to the diagram, the pipeline moves from the yellow processing machine directly into this big blue database. And the standard explanation I always hear is that tokenization breaks language down into mathematical puzzle pieces.
Yeah, that's the common analogy.
But I kind of want to push past that basic definition today, because tokenization is often framed as a destructive process. Like, it sounds like taking a beautiful tapestry and putting it through a wood chipper to get a pile of disconnected threads.
Well, the wood chipper analogy implies a complete loss of structure, which is actually inaccurate.
Right. If we are breaking language down into these tiny robotic tokens, how does the final output end up sounding so poetic and fluid?
It's because the tokens aren't destroying the language. A more precise visualization is a highly advanced loom unweaving the tapestry.
Unweaving it. Okay, I like that.
The process doesn't destroy the relationship between the threads. It just translates those threads into a medium that a machine's mathematical architecture can actually manipulate.
Because a machine processor doesn't understand the concept of a word.
Right, exactly. It only processes numerical values and high-dimensional vectors. Tokenization is literally the mapping of semantic meaning to a numerical identity.
So we are assigning specific mathematical identifiers, the tokens, to words, subwords, or sometimes even individual characters.
Yes. But the crucial part of unweaving that tapestry is that the system preserves what we call the positional encoding.
Positional encoding. That means the specific sequence and proximity of those tokens are what actually give them meaning, right?
Exactly. Positional encoding is the absolute secret to retaining the structure of the language. When a sentence is tokenized, the model doesn't just record the numbers willy-nilly.
It records their exact spatial relationship to one another.
Right. So the word apple becomes a numerical token, but its relationship to the token for tree or the token for pie is preserved in how the data is spatially structured.
Okay, so once the entire corpus of human text is unwove, normalized, and converted into these numerical tokens, it flows out of that processing machine.
And it gets stored in that massive blue database cylinder depicted in the diagram.
Got it. So that blue cylinder essentially represents this vast reservoir of structured numerical relationships.
It is no longer a collection of books or articles or code snippets. It is this incredibly dense, multidimensional matrix of tokens, and it's prepped and ready for ingestion by the neural architecture.
Which brings us to the absolute visual centerpiece of the level up coding diagram.
The glowing brain.
Yes, the glowing brain. The pipeline flows out of the blue database cylinder and directly into this massive, pulsing blue brain sitting atop a complex geometric machine base.
We are fully leaving the data preparation phase now and entering the core engine of the system.
And the text, pointing to this glowing brain, highlights two distinct functions. It says, applies token prediction techniques and learns language patterns.
Those two labels are so important. They represent the absolute foundation of large language model architecture.
Why are they separated like that?
Because they highlight the division between the underlying state of the model, which is the learned patterns, and the active process of inference, which is the prediction.
Okay, let's separate those two concepts for a minute, starting with learns language patterns.
Sure.
The glowing brain draws from that vast matrix of tokens in the blue cylinder to establish its parameter weights.
Right. And it's important to note, it isn't just memorizing dictionary definitions. It is mapping the statistical relationships between billions of concepts.
So it learns the rhythm, the syntax, the grammatical rules, and even the logical progression of human arguments.
Exactly. This learning phase, which is essentially the training of the model, is the creation of a high-dimensional vector space.
High-dimensional vector space. That sounds intense.
It is. Every single token is assigned a position in this space based on its context within the training data.
So the model learns that the token representing the word king has a specific mathematical relationship to the word queen.
Yes. Just as man relates to woman, the patterns it learns are quite literally the mathematical distances and directions between tokens in this incredibly complex landscape.
It's essentially constructing a topological map of human meaning.
That's a beautiful way to say it. A topological map.
And it doesn't inherently understand what a galaxy is, for instance, but it knows exactly where the token for galaxy sits in relation to stars, gravity, and telescope within its map.
Right. It doesn't have conscious comprehension, just spatial relation. And that topological map is the foundation.
Okay, so then what about the second label, applying token prediction techniques?
That is the mechanism of action.
Hmm.
When the model is running, it actively traverses that map we just talked about.
So it takes a sequence of input tokens, calculates the probabilities based on the patterns it learned, and predicts the statistically most likely token to follow.
Yes. And that prediction mechanism is precisely what generates the illusion of intelligence.
I want to focus on that for a second,
Hmm?
because when I prompt the model with a complex question, it feels like it's thinking.
It really does. But it's not reasoning through the logic of your query at all.
Right. It's essentially the world's most advanced, high-stakes game of autocomplete on your phone.
Yes. It evaluates the sequence of tokens you provided, references its vast mathematical map of language patterns, and calculates the highest probability path forward, one token at a time.
It generates the response sequentially. That's crazy.
And this distinction between learning patterns and predicting tokens, it really forces us to reevaluate what it means for a machine to actually know something.
Yeah, because the model doesn't possess factual knowledge in a human sense.
Not at all. It possesses the statistical shape of knowledge.
The shape of knowledge. I love that phrasing. So if you ask it to explain quantum mechanics, it isn't retrieving a stored file on quantum mechanics.
Nope. It is merely predicting the sequence of tokens that most closely mirrors the patterns of how human physicists have written about quantum mechanics in the past.
Wow. The model knows the shape of a fact. That concept completely recontextualizes the whole phenomenon of AI hallucinations for me.
Oh, exactly. Hallucinations make perfect sense when you look at it this way.
Because if a model hasn't ingested enough data to map the precise relationships of a niche topic, it doesn't recognize its own ignorance, does it?
No, it has no self-awareness of what it doesn't know. It simply continues its core function, which is predicting the most mathematically probable next token.
Based on whatever adjacent patterns it does happen to have. So hallucinations are not a glitch in the system at all.
Not a glitch. They are the system functioning exactly as designed, just operating in a localized area of sparse data.
That is fascinating. The prediction engine never stops running.
Right. If the topological map is blurry in a certain area, the model will confidently traverse that blurry space anyway.
And it ends up generating a sequence of tokens that sounds grammatically perfect, but is factually entirely unmoored from reality.
Exactly. The glowing brain is basically an engine of statistical mimicry. Its ability to maintain the illusion of being a conversational partner is entirely dependent on the density and quality of the patterns it learned during training.
So basically, we've got this massive, brilliant brain. But looking at the level-up coding diagram, the raw foundational brain is not the final product.
No, far from it. It's too chaotic.
Right beneath the glowing brain, integrated directly into the metallic base, is a control panel featuring physical switches and sliders.
Yeah, this phase represents the necessary constraints and adjustments you need to take a theoretical architecture and actually deploy it in the real world.
The labels pointing to this control panel read model compression and fine-tune and adapt given specific domains. Let's start with compression,
Okay.
because the necessity of model compression highlights a massive bottleneck in artificial intelligence.
It's the elephant in the room for AI developers.
We just spent all this time establishing that the power of the model comes from the sheer scale of its training data and the complexity of its map, right?
Right.
It takes warehouses full of highly specialized processors pulling staggering amounts of electricity just to train the network. So why invest all of those resources to build a massive neural architecture only to immediately compress it?
It seems counterintuitive, right?
Yeah. Doesn't making it smaller mean we're stripping away some of its smarts? Doesn't shrinking the model inherently degrade the nuance of its predictive capabilities?
It does, but the tension between scale and deployment is the defining engineering challenge of the field right now.
How so?
Well, a fully uncompressed, state-of-the-art model possesses incredible emergent capabilities, but the compute cost to run inference, meaning to actually generate answers, is astronomically high.
Oh, so it's a hardware limitation.
Entirely. If a model requires an entire server rack to answer a single user query, It cannot be deployed to millions of simultaneous users on an app.
The hardware realities literally force the compression. You have to shrink it down so a regular person can access it.
Yes, and model compression utilizes highly complex techniques like quantization and pruning.
Pruning, like trimming a tree.
Exactly like that. Pruning involves analyzing the neural network and identifying the parameter weights that have the absolute least impact on the final output.
And then it just systematically trims away those redundant pathways,
Yep. And then you have quantization, which actually reduces the mathematical precision of the numerical values representing the weights.
which effectively shrinks the digital footprint of the entire map. It's an incredibly aggressive optimization process.
It is. You are stripping away the least useful connections to reduce the computational overhead.
But there has to be a threshold where pruning goes too far, right? Where the model just loses its coherence.
Oh, absolutely. There's a constant balance being struck by engineers. Compression sacrifices a degree of raw, high-resolution nuance in order to gain computational efficiency.
Distilling it down.
Right. The goal is to distill the vast parameter space into a nimble format that retains the core accuracy without requiring a supercomputer to run.
Okay, so once the model's compressed to a deployable size, we reach the second function on the control panel.
Fine-tuning.
Yeah, fine-tune and adapt given specific domains. And the diagram uses the visual of sliders for this, which I think perfectly encapsulates the concept of adjusting parameter weights.
It really does, because a foundational model, out of the box, is a generalist.
Since it learned the patterns of the entire internet, it can write a poem, explain a plumbing issue, or summarize a historical event with equal statistical probability.
Right. But a generalist model often lacks the hyper-specific accuracy required for specialized tasks in the real world.
So fine-tuning is the process of steering that latent space.
Yeah.
You take the foundational model, which already understands the structure of human language, and you subject it to a secondary training phase.
Exactly. Using a highly curated data set this time.
Right, like if the goal is to deploy an AI for medical diagnostics, the developers will fine-tune the model on millions of medical journals, clinical trial data, and pharmacological texts.
And this secondary training forcibly adjusts those parameter weights we talked about. It shifts the topological map so that the model prioritizes the patterns found within that specific medical domain.
You are literally sliding the weights, like adjusting the equalizer on a stereo.
Great analogy. The model still knows how to construct a grammatically perfect sentence, but its prediction engine is now heavily skewed toward generating sequences that align with medical expertise.
It becomes a specialist.
Yes. The combination of compression and fine-tuning transforms the unwieldy generalized brain into a targeted, efficient tool.
However, the diagram reveals a really critical step that must occur before that specialized tool can actually interact with the public.
It is safety net.
Yeah. Moving slightly to the left in the diagram, plugged directly into the base of the machine via this thick black cable, is a separate, dedicated computer terminal.
It features a monitor, a keyboard, and a little joystick.
And the label explicitly states its function: blocks harmful, offensive, or biased content.
The visual execution of this element is vital for understanding the current limitations of AI architecture. Notice where it is.
Yeah, it's totally separate. This safety filter is not integrated into the glowing blue brain itself. It is not part of the metallic base.
It is an entirely external monitor acting as an intermediary step.
It's like a post-processing Band-Aid.
Correct.
Or like a security guard or a bouncer at the door of the club.
Exactly. The model generates its output, and that output is routed through this external checkpoint before it ever reaches the user.
The architecture of the diagram really forces us to ask why this external bouncer is necessary in the first place.
And the answer to that traces all the way back to the very first step of the pipeline, the raw harvest.
Right, because the model ingested the internet. It absorbed humanity's collective text, which includes our most profound discoveries, but also our most toxic biases.
And the neural network mapped all of it equally. From the perspective of the glowing brain, a sequence of tokens representing a hateful slur is just as mathematically valid and structurally sound as a sequence of tokens representing a recipe for bread.
Oh, wow. Yeah, because the neural network is essentially a black box of amoral math.
Exactly. Amoral math. It does not possess a conscience, it has no ethical framework, and it has zero understanding of social consequence.
It simply calculates the highest probability token sequence based on the prompt and its training weights.
So, If a user prompts the model with a heavily biased premise, the model's uninhibited mathematical function is to flawlessly predict and replicate the bias inherent in its training data.
It just holds a mirror up to us. So the external safety terminal exists because the core architecture literally cannot self-regulate its ethical output.
Right. It needs a babysitter. The safety terminal represents a secondary layer of programming. It often uses deterministic rule sets or smaller, specialized classification models.
So as the main brain generates its sequence of tokens, this external monitor inserts the sequence in real time.
Yes, it acts as a heuristic filter. It scans the incoming vector sequence for patterns that strongly correlate with known toxic, harmful, or biased structures.
And if the external terminal calculates a high probability of harm.
It intercepts the output. It essentially blocks that specific vector path and forces the generation engine to reroute, producing an alternative, sanitized sequence.
The fact that we have to build an entirely separate piece of machinery just to filter the output of the primary machine, that really highlights a fundamental challenge in artificial intelligence, doesn't it?
It really does. We engineered this incredibly powerful system to mimic human language, and now we must rely on secondary algorithms to suppress the darkest reflections of our own data.
It's a sobering thought. But that safety terminal is the critical barrier between raw, uninhibited statistical mimicry and a viable, deployable product.
It is the final checkpoint, and after it passes that, we reach the ultimate destination.
The final mile of the journey, located at the bottom left of the flowchart.
The data path moves past the external safety terminal and connects directly into a series of standard, everyday laptops.
And the final labels pointing to the laptops read, processes user queries, and generates coherent responses.
The diagram beautifully collapses this massive industrial scale down to the individual user level right there.
It really grounds the whole process. All of those multi-tiered servers, the complex normalization, the multidimensional vector mapping, the external filtering.
It all culminates in a single, simple text box on a consumer laptop.
Let's trace that full sequence in real time to bring it all together. You sit at your laptop and type a query.
That text is instantly transmitted and enters the pipeline.
It hits the refinery, where your specific query is normalized and tokenized, meaning it's mapped into numerical vectors.
Right, and those input vectors trigger the inference engine within the compressed, fine-tuned model.
The model then evaluates the mathematical trajectory of your input against its vast topological map.
It begins predicting the most statistically probable sequence of response tokens.
Those tokens are generated, intercepted, and evaluated by the safety terminal.
And once the sequence clears the heuristics filter, it is decoded, translated from numerical tokens back into human text, and transmitted back down the wire to your screen.
And the entire progression happens in milliseconds. It's truly astounding. But you know, the most revealing word in that final label is coherent.
Oh, definitely. Notice what it doesn't say.
Right. The label doesn't say generates intelligent responses or generates factual responses. It explicitly says generates coherent responses.
Coherence is the ultimate triumph of the architecture.
Because after all the brute force processing, the mathematical unweaving, the probabilistic calculation, and the algorithmic filtering,
the system consistently produces strings of text that mimic the logical flow and syntactical structure of human thought. The magic is simply the sheer reliability of that coherence.
when you look at the level-up coding diagram in its totality, the blinking cursor on a laptop screen takes on entirely new meaning.
It really does. It ceases to be a simple user interface.
Yeah, it becomes the exhaust port of a colossal computational engine. We have traced the data from the sheer brute force of the raw harvest through the mathematical translation of tokenization into the latent space of the prediction engine.
Past the required constraints of compression and safety filters, and finally into the hands of the user.
Deconstructing the flowchart really removes the mysticism surrounding large language models.
I hope it firmly establishes the technology as a triumph of data engineering and statistical probability rather than, synthetic sentience.
Exactly. And understanding the mechanical reality doesn't diminish the achievement at all. I think it actually deepens the appreciation for the architecture required to make a machine speak.
It really is a modern marvel.
Well, thank you for joining us on this deep dive. And a huge credit again to Level Up Coding and Nikki Siapto for creating the visual roadmap that guided our analysis today.
Yes, incredible work on their part. Their flowchart brilliantly exposes the heavy machinery operating beneath the surface of the text box.
But before we conclude, I want to hand it over for one final thought regarding the implications of this pipeline, something to leave you mulling over.
Yeah, so we've spent this time meticulously analyzing how a model learns patterns and predicts tokens based on existing human data, right?
Right.
Well, I want to leave you with a structural question to consider. If the core engine of this glowing brain functions strictly by calculating probabilities based on what humans have already written in the past,
Okay.
is it mathematically possible for this architecture to ever generate a truly original, groundbreaking thought? Or, by the very nature of its predictive design, is it constrained to forever function as a highly advanced, brilliantly compressed remix of human history? Something to think about.